Right, welcome to another Math 2417 review. Today we'll be going over some limits at infinity, which we touched on last week. We'll talk about optimization, and lastly we'll talk about differentials. So, we'll start off with limits at infinity. And if you can recall from last week, if we had a top-heavy function, and of course we're considering for all of these the limit as x goes to infinity of some function f of x. If we had a top-heavy function, then our limit would go to positive or negative infinity. If we had a bottom-heavy function, the limit would go to 0. And of course, when I'm talking about top-heavy and bottom-heavy, the top-heavy function, I mean a function that's got like a greater power of x on top than on the bottom. So here we've got a squared over just next to the first. This is top-heavy. Bottom-heavy function would be like the reverse, where the greater power of x is on the bottom. And lastly, if we have a balanced function, we would need to look at the coefficients. And we just touched on this, talked about all of this last week. An example of a balanced function would be like x squared plus 3 over 4x squared minus x, and its limit is equal to 1 over 4, because we just look at the coefficients on the largest terms. So we look at the x squared, and also at this 4x squared. And that's just a 1x squared over 4x squared, which becomes 1 over 4. That is our basic limits at infinity. If we wanted to talk about more formal definitions, you could say that the limit as x goes to infinity of some function f of x is a real number L if for every, this is the epsilon delta proof of limits at infinity, so if for every epsilon greater than 0, there exists an n greater than 0 such that x being bigger than n implies that the magnitude of f of x minus L is smaller than epsilon. And really all this is saying is when this n term gets very large, x has to be bigger than n. So when x is very large, let's say we've got a function, and it has some limit L that's represented by this dashed line. And as x gets larger and larger, the difference between the actual function value and the limit gets smaller and smaller until it's basically an infinitely small gap between them. And that's basically what this epsilon definition of a limit at infinity is. I won't do an example of this one. I don't think you should need to prove it in this class at all. I'll do an example of next one though. And this is if we have a function whose limit goes to infinity. We say that the limit of a function is equal to infinity if for every m bigger than 0, there exists an n bigger than 0, such that f of x is bigger than m whenever x is bigger than n. And all this is saying is if we have some kind of function and it goes to infinity, no matter what value of m we pick, we can pick a big value of m. If this is m, just the line y equals to m, at some point, every x value past some line n is going to be bigger than this m value. You can see our function value past this point n here is always going to be greater than this m value that we pick. And this is true for any m. If we wanted to do a brief example of this, what we can do is, give us enough space. Let's say we wanted to show that the limit as x approaches infinity of x squared equals to infinity. Well, then we can say, let our m value be equal to x squared. Then x is equal to the square root of m. But we know we can let, actually we want to start off by taking f of n. So we want to let f of n is equal to, just plug an n in wherever there's an x. So if we let m equal to n squared, then then n is equal to the square root of n. And then we can choose that to be our n value for any m that we're given. Then we know that n is smaller than x, so the square root of m is smaller than x because n and the square root of m are the same thing. So m is smaller than x squared whenever x is bigger than n. So that is our proof. We showed that for any m value we can pick, we can find an n, so that whenever x is bigger than n, x squared is bigger than our m value. As far as some practice, I'm not going to make you practice any of these formal proofs, but I will give you a couple more practice problems with just generic limits at infinity. You don't have to prove any of these, just find the limit. All right, go ahead and try those ones out. These ones are a little harder than last week's, but I think you can do them. That a is infinity, b is 1, c is 1, and d is 0. All right, let's go over those. A, if you look at the powers on A, you can see that our largest terms are going to be this 4th root of x to the 7th and this 5th root of x to the 7th. And if we wrote that in fraction terms, that would be an x to the 7 over 4, or x to the 7 over 5, and 7 over 4 is bigger, so this is top heavy, so it would be infinity. For B, B is a little trickier because if I rewrite it as the limit as x approaches infinity, we can say that the first is x to the 2 over 6 minus x over, again, x to the 2 over 6 plus 2x. But in this case, 2 over 6 isn't our x to the 2/6 isn't our largest term. You can actually see that this x here and this 2x here are going to be our largest on top and bottom. So this one is actually -1/2. That's a bit trickier. Just make sure you're identifying the largest terms on top and bottom, because they're not always going to be written at the front. Part C, this one is a bit trickier, probably because I don't think you've necessarily learned the pattern of natural log of x, or what we consider it to be. We would actually consider, we know that x is always bigger than the natural log of x. So with regards to looking at the highest order term, we would actually say that x is going to be of a higher power, quote unquote. It's not really literally that, but essentially this x function grows infinitely faster than this natural log of x function. And because of that, this one, C, is actually bottom heavy. So this one is equal to 0. And for D, again, we need to look at our largest power on top and bottom. On top, we're going to have the square root of x cubed multiplied by the square root of x. On the bottom, we're going to have x to the 5/2 multiplied by this positive 2. So our largest power on top is going to be the square root of x to the 4th, and on the bottom, it's just going to be 2x to the 5/2, and this is also bottom heavy. So its limit is also 0. Does that make sense? Cool. All right then, let's go ahead and move on from here to our second topic, which is optimization. Okay, so if you recall, when we take the derivative of a function, it lets us find maximums and minimums, correct? Yeah, so with optimization, we could use the first derivative of a function. If our function represents something like volume, then the first derivative would give us locations where we could have maximum volume and minimum volume, right? Yeah. So actually, this is actually something that crops up a decent amount in calculus, using the first derivative to maximize or minimize function value. So for example, let's say we have a box and it's going to have a square base, and no top. So I will draw this as best as I can. And we'll call that a box. And it has no top and the base is square. So we can call the length of each base x and the height h. And this box can be made up of up to 108 inches squared of material. So we can say that its surface area is equal to 108. And its surface area is also equal to x squared plus 4 times s times h, because x times h is going to be the area of this side here, and we've got 4 of those sides, plus the area of the base, which is x squared. Additionally, we know that the volume is going to be the length times width times height, so x times x times h, which is x squared times h. So if we wanted to optimize our volume, we would need to take the derivative of volume in order to find where its maximums and minimums are. However, right now our volume function has 2 variables, the x and also the h here. And we only know how to take the derivative of a function of 1 variable. That's where this second equation comes in, the surface area equation. We know that 108 is to x squared plus 4xh. So if we rewrote that to get h by itself, we would get that h is equal to 108 minus x squared divided by 4x, correct? So if we substitute this h here into our volume equation, we get that our volume is equal to x squared times 108 minus x squared divided by 4x. So then our volume is equal to, that would be 108 times x squared over 4x, which is, I will actually just keep it like this. This becomes 108x minus x cubed divided by 4 if we cancel out an x on top and bottom like this. There. So we can take the derivative of this volume function and we get that the first derivative is 108 divided by 4 minus 3 over 4 times x squared. And all I did there is I said e equals, just by breaking apart my fraction, and then I took the derivative of that. And to find our maximums and minimums, we want to find where this function is equal to 0. 108 divided by 4 is just 27 minus 3 over 4 x squared. So then 3/4 x squared equals to 11 if we add it over. So then x squared is equal to, divide both sides by 3 is 9, multiply both sides by 4 is 36. So then x is positive or negative 6. But since in this case x represents a side length, our x value has to be 6. And if we wanted to check that that was a maximum, again, we could just put that into our first derivative. So we have a v prime number line. And then at 6, when x is smaller than 6, we get that our first derivative is positive. And when x is greater than 6, 27 minus 3/4 x squared is going to be, the x squared is going to outweigh this 27. So we're going to have a negative. Positive changing to a negative is a max. So we know that x is equal to 6 is one of our dimensions, and because of this h equation, right up here we can find our h value. So we know that x is equal to 6, and h is equal to, I forgot the equation, 108 minus x squared over 4x. So in this case, 108 minus 36 all over 24, which is 72 over 24, which is 3. So then the dimensions of the box would be base being 6 inches by 6 inches, and then height of 3 inches. That would be our optimized volume. Does all that make sense? In this case, it wouldn't make a whole lot of sense to find the minimum volume, because all you would have to do is say, well, I'm just going to let the height equal to 0, because then it's going to have 0 volume. So in this case, yes, you only need to find the maximum, because the minimum doesn't make sense in this context. And of course, it'll depend on the problem. So for example, if we'd flipped the positions and said the box needs to have a minimum volume of this much, and minimize the amount of materials needed, so minimize the surface area, that would have been like a flipped question. But in that case, we would have needed to find a minimum. Does that answer your question? Cool. So, in general, there are a couple patterns you'll see with regards to optimization. We'll have two equations. One of them is going to be called your primary equation. And this one is usually a function of two variables, and it's the one that you'll be taking the derivative of. So in the previous example, our primary function, primary equation, was this volume equation right up here. We took the derivative of volume because volume was what we were trying to optimize. That's how you can tell which one is the primary equation. It has the value you're trying to optimize. Then we have a second equation. I like to call it the constraining equation, or the constraining equation. And this is usually the function that limits like your materials. So in this case, our constraining equation was the surface area equation, because it told us that we could have up to 108 square inches of material to work with. And what you do with the constraining equation is you use it to substitute one variable out of your primary equation. So in the previous example, what we did is we had our primary equation, this volume equals x squared times h, and our secondary equation, our constraining equation. And you'll notice we actually took this constraining equation and solved for h in terms of x. And we took that h value and substituted h out of our volume equation. And then our volume equation was an equation of one variable, so we could take the derivative and find its maximums and minimums. So that's the general process you'll use for optimizing. I'll go ahead and give you a practice problem now. So we'll start with something that's maybe just a little more less problemy. Let's say you have a semicircle, kind of like so. It's almost a semicircle. And you have some rectangle in it, like this. And you want to maximize the area of the rectangle. And this rectangle is bounded by x-axis and the function y equals to the square root of 25 minus x squared. So we want you to maximize the area of the rectangle. Think you can try that one? I'll give you a few minutes to work on it. Right, how's it coming? Stuck on finding critical numbers? All right. Well, how about I start working it out, and then if I do anything different than you did, give me a quick shout out. How about that? So first off, we need to find out what our primary and constraining equations are. Our primary equation, well, it needs to have what we're trying to optimize in it. So in this case, we're trying to maximize the area, so it's going to be our area equation. In this case, the area is going to be this height, so y, times this length, this width, which is x plus x, since each of these are our x values. So y times 2x, which is 2xy. And then our constraining equation is going to be nothing more than what's actually given. So y equals to the square root of 25. That is not 25 of 25 minus x squared. So then what we need to do is substitute y out of our primary equation. So our area is 2x times the square root 25 minus x squared. Did you get up to here okay? Yeah. If you use just xy for area instead of 2xy, the numbers don't come out quite so nice. But if we kept moving on, from here we would get that our first derivative, a prime, is 2 square root 25 minus x squared. I'm using the product rule here. And then plus 2x times the derivative of the square root of 25 minus x squared. We're going to need to use the chain rule. It's 1 divided by 2 because of the power rule, square root 25 minus x squared times the derivative of 25 minus x squared, which is negative 2x. And if we simplify that, we get that's 2 times the square root of 25 minus x squared. This 2 can cancel with either of these two, so minus 2x squared divided by the square root of 25 minus x squared. So that is our first derivative. To find the critical points, we need to let that equal to 0. So 0 equals 2 square root of 25 minus x squared minus 2x squared divided by square root of 25 minus x squared. Now, if we multiply both sides by square root of 25 minus x squared, well, 0 times the square root of 25 minus x squared is still 0. Then we would have 2 times 25 minus x squared, not in a square root, minus 2x squared, because this 25 minus x squared and this 25 minus x squared would cancel and just result in 1. Then if we distribute, we get that 0 equals 50 minus 2x squared minus 2x squared, or in other words, 4x squared equals to 50, so x squared equals to 25 over 2, so x is plus or minus 5 divided by the square root of 2. But again, in this case, we could have a negative x, I suppose, so we should probably check with a number line to make sure we're finding a maximum value and not a minimum. So we'd want negative 5 divided by root 2 as one of our critical points, and plus positive 5 over the square root of 2. Are you with me so far? So again, our first derivative is this function right up here. If we plug in a negative 5, for instance, we would get actually we couldn't plug in a negative 5. If we plugged in a number that is negative 4, we'll say, then we would get 2 times the square root of 9. So 6 minus, that would be 2 times 16, 32 divided by 3. That's a little over 10. So 6 minus a little over 10 is going to be negative. And then if we plug in 0 for our first derivative, we would get 2 times 5 minus 0, which is positive. And then again, if we plugged in a positive 4, that would again get us a negative number. So we would have negative, positive, negative. This here is a minimum, and this here is a maximum. So that tells us that our x value, in order to maximize the area, should be 5 divided by the square root of 2. And we know that y is equal to the square root of 25 minus x squared. So our y value is equal to the square root of 25 minus 25 over 2, which is also equal to the square root of, 20, which is equal to 5 divided by the square root of 2. So the length of our rectangle is going to be 2x, which is 5 square root 2, and the height of our rectangle is going to be y, which is 5 divided by the square root of 2. Make sense? Cool. All right, would you like to try one more optimization problem, or should we move on? Another one? All right. Go ahead and clear the whiteboard. Get a little more space. So a rectangular page needs 24 inches squared of print. And it also has 1.5 inch margins on top and bottom, and 1 inch margins on the side. So a page got print in the middle, then this top margin is equal to 1 and 1/2, and the side margins are equal to 1 inch. And we want you to minimize the area of the page while still maintaining that it has 24 inches squared of print on it. How's it coming? Well, that's unfortunate. What did you get for your primary equation? E4 equals to 6x squared. Not quite. In this case, we don't necessarily, let's see, the 24 is our constraint, right? Actually, yeah, 24 is our constraint because we're trying to minimize the total area of the page. So I'm going to start with defining some variables. We're going to say that this is x and this vertical. So then this 24 needs to be equal to x times y, right? Because that's the area of our point. This is our constraining equation because it uses this 24 inches squared of print. For our primary equation, we want to take the equation using the whole area of the page. In that case, that's going to be x plus 2 for this whole length across this whole page. And that's going to be multiplied by the whole vertical length. So y plus 3, because we have 1.5 inch margin on the top and 1.5 inch on the bottom. That's going to be equal to our a value. This is our primary equation. Does that make sense? Cool. So what should our next step be? We could try finding the derivative, except right now, this is still a function of x and y, right? So we need to reduce it to a function of one variable. How would we do that? Um, but that would still be in terms of x and y. This is where a constraining equation comes in, right? We can actually take this x times y and say, okay, because that's still right, I don't want to use because 24 is equal to x times y, you can say that y is equal to 24 divided by x, right? And then we could take this and substitute it in to our equation. Does that make sense? Yeah, because now this is a function of just x, so we can take the derivative, right? Yeah. In this case, x times 24 over x is 24 plus 3x plus 48 divided by x plus 6 is equal to a if we distribute. So now if we take the derivative, we don't have to use the product rule. we can say that the derivative of a is just 3 times x minus 48 over x squared. And then we set that equal to 0 to find our critical points. So then 0 equals 3x minus 48 divided by x squared. So 48 divided by x squared is equal to 3x if we add the 48 over x squared over. So then 48 equals to 3x cubed. And see, I'm doing something weird here. Yes, I took my derivative wrong. That should be just a 3 there. That's why. Because the derivative of 3x is just 3. And that would, of course, make this equal to 3x squared. So x squared equals to 16. X is positive or negative 4, but again, the negative value doesn't make sense. So x is equal to 4. Does that make sense? And then to find our y value, again, we just look back at this equation we used to substitute y out. In this case, it is y equals to 24 minus x. Since x is equal to 4, y is 24 divided by 4, so y equals to 6 inches. And x is 4 inches is our answer. Does all that make sense? Have you covered this in class at all? I'm just wondering if you're ahead of the syllabus, behind the syllabus. Went over it a little bit. Okay. Yeah, that was said you were supposed to go over optimizations this week, or this last week, sorry. So go ahead and put those in the review. There is one other topic for today, and that is differentials, which is not all that bad. Have you seen problems like use differentials to approximate the square root of 4.1? No? Okay. In that case, yeah, your class might be a little bit behind. I'm trying to pull up the syllabus right here. Having a bit of trouble. Oh well. We'll just go over this really briefly in the last few minutes, unless you want to go over something else. Would you like to review something else? This is fine. All right. I'll just go ahead and give you a really brief introduction. A differential is basically just a very small change. Usually just in one variable. So it's also approximate. So if we have some function f of x and we took its derivative, then that would be f prime of x times dx. and that would be equal to dy. We say that these are essentially like differentials. It's how our notation looks. In terms of problems, I think we'll actually just go through an example problem because it makes things considerably easier to understand. And we've actually got one right here. So we'll go ahead and work through this problem here. Use differentials to approximate the square root of 4.1. So first, what we need to do is write a function so that we can take the derivative. And in this case, we're approximating a square root. So we'd say our function is the square root of x. And we need, secondly, a point that's close to this 4.1 value. So I'm going to say that 4 is close enough to 4.1. Then we say that our exact change in x, delta x, is equal to 0.1. And we're going to refer to this as dx. Then if we take our derivative, that's 1 divided by 2 times the square root of x dx. And we can refer to this as a dy. In other words, our change in is equal to this small change in x times our derivative value. Is this all making sense? Can you still see my screen actually? Looks like it might have cut out. Um, let's see. Second. There we go. Okay. So we can say that our change in y is equivalent to our first derivative at our point multiplied by our small change in x. In other words, we can say that dy is equal to 1 divided by 2 square root. We're going to use the c value of 4 times our dx, which is 0.1. And the square root of 4 is 2, so 1/4 times 1 over 10, which is 1 divided by 40. And essentially, we say, if we went ahead and drew out a function graph, that's not right, but okay. Basically what we're doing is we have our point here, and this is at exactly 4. And we know that it has a y value of 2. What we're doing is we're saying 4.1 is very close to 4. So if I can approximate this tiny little gap here, dy, and I can approximate that using this tiny little change here in x by using the first derivative, then this y value occurring right here is going to be this x value, sorry, this function value here, plus our change in y. So we know that f of 4 is equal to 2. So then we can say that f of 4.1, or the square root of 4.1, is going to be very close to 4 plus our change in y. And that's 2 plus, we found our change in y, which is 1 over 40th. And the actual function value, or in a decimal format, that's 2.025. We say that this is approximately equal to the square root of 4.1. And in case you're interested, the actual square root of 4.1 is 2.0248. So we were off by about 2/10,000ths, right? That is off by just 0.0002. That's a pretty good approximation. But does all of this make sense? How did I get the f of 4 plus dy? I gave a brief explanation with this graph over here. I can say if this black dot right here is f of x, and this red dot is a point very close to it, then I can approximate this red dot by adding very small changes or differentials to this black dot. Does that kind of make sense? Yeah. You can maybe think of it in terms of a tangent line. For instance, our general tangent line equation is the tangent line of some function is f prime at some point c times x minus c plus f of c, where c is the point that we're making our approximation at, right? Or the center of our tangent line. And essentially all it looks like is if we've got some equation like this, that would be our tangent line, and our point is centered at x is equal to c. Well, if we have an actual x value, like right here, then this x value minus the c value is going to give us this tiny distance from here to here. In other words, x minus c is our change in x. And this f prime of c is actually that same f prime of c we saw up here, right? Here we had f prime of 4, which gave us 1/4. And we can actually see that f prime of c times our change in x is our dy, and then this is our f of c, which is essentially our initial value here. So our small change in x is just our literal y value plus a change in y. So that's kind of where it comes from. There are more rigorous, I guess, definitions of it, but this is kind of how I like to think of it because it's a little easier to grasp. Does all of that make sense? Yeah, no problem. Since you haven't covered this in class, I don't want to get too into it, and we're just about out of time anyway. So I don't think we'll do any practice problems or any more examples this week, but we'll definitely try to cover it a little more next week. Sound good? Cool.